So people online can put on. Oh, no, okay. I think we'll start.
Okay. People in the waiting room? Are there people waiting in the Zoom?
No, now it started. So I logged in, so just my screen changed. Okay, perfect. So then I think we're ready. This week it's our honor to have Miguel Sánchez-Conde visiting. He's interested in dark matter, studying with the help of gamma rays. He's in several collaborations, including Fermi LAT, and he did his PhD in 2009 in Canada.
Yes.
And then a few postdoc stations followed in the Canary Islands, in the US, Stanford, and in Sweden, Stockholm.
Mm-hmm.
And then he came back to Spain, and now he's a professor in Madrid. Yes, and he will tell us about probing dark matter with the help of dark matter annihilations. And yes, it's an honor, Miguel, to have you here. We're looking forward to your talk. The stage is yours.
Thank you so much, Maurice, for the nice presentation. And thank you so much, guys, for coming. Good morning, everyone. Thank you also, Raúl and Silvia, for the nice invitation. It's amazing that I didn't come here for 7-8 years, so it took 7-8 years to come here. So I'm sorry about that, guys. But finally, we made it. Yes, so my pleasure once again. I mainly work on dark matter searches, and in particular using gamma rays. Although we also use cosmic rays and neutrinos for that, but we're mainly we're mainly focusing on gamma rays. As Maurice was saying, I'm also a member of Fermi LAT. My group and I have been deeply involved in Fermi LAT analysis for a long time now, and playing also important roles in the collaboration and so on. So my hope is actually to give you some hints about the things that we have been doing in the last few years. And in particular, when thinking about the seminar and things that could be actually of interest for you guys, given the more or less the focus of your work, I thought it would be interesting to take a look at what we have been doing when it comes to dark matter searches, and in particular to understand the role of dark matter halo substructure in these dark matter searches that we are currently doing in gamma rays. And for that, I will be focusing on our gamma ray efforts, paying some attention to the gamma ray analysis and how we actually set, we first look for radiation signals, and how, in the absence of these signals, we set valuable constraints on the dark matter parameter space. And also, in parallel, I will be talking also about the numerical modeling that we perform when it comes to the tiny guys in the universe, this clumpy substructure, right? And once again, the role of all this numerical modeling to drive our search in gammas. Okay, so yeah, I will be brief in the introduction, although I hope it will be self-sufficient, but of course, let me know if you have any questions, especially the young people here, because I understand there's some kind of intersection between my field and your field, guys. So I don't think I need to convince this audience about this thing that I put here, right? That we believe at the moment we believe that the visible matter in the universe is just the tip of the iceberg. Indeed, we have been accumulating evidence of this non-baryonic form of dark matter for almost 1 century now. Of course, I'm not going to go into the details of all this plethora of observations, right, and accumulated evidence. But let me just give you the take-home message, which is actually relevant for the remainder of the talk, and it's the fact that this evidence has been reported at all scales, no matter what you do in cosmology, right, and astrophysics. But it's only astrophysical as of today, and this is actually important, especially when it comes. Well, maybe this is obvious for you guys, but not so relevant, so obvious for instance, particle physicists. They look for dark matter also at the lab, but actually all the motivations that they have at hand is actually astrophysical, although they are doing particle physics and they search for this dark matter at the lab. Once again, all the evidence that we have at the moment to believe on this dark matter is astrophysical and only astrophysical as of today, right? There's nothing really in the standard model of particle physics that to think about this dark matter. Okay, so we have a lot of evidence to believe on this non-baryonic form of dark matter. But when it comes to the true nature, the ultimate nature of the dark matter particle itself, we are totally lost. We don't have a clue about this dark matter particle properties, right? And this is, I think, nicely illustrated. This lack of knowledge that we have is nicely illustrated in a plot like this one, where you can actually see something that is that relates to the cross section of the interaction between the dark matter particles that you would like to consider, and versus the mass of the dark matter particle, right? Each box here will correspond to a different candidate coming from particle physics to constitute the dark matter in the universe. And I don't know if you guys see this correctly, but this spans over, I don't know, like 50 orders of magnitude here in the x-axis versus 60 orders of magnitude here in the y-axis. Basically, this means that we have, again, no idea at all about the nature of the dark matter, and it can be basically anything, right? Indeed, in the standard model of particle physics, there's no viable candidate. The only non-baryonic candidate that we have there is the neutrino, and of course we know that this is not, it's not possible for the neutrino to constitute the whole dark matter content because of the masses, mainly, and also because it's hot, right? And you need something really cold. But of course, as soon as you go beyond the standard model of particle physics, a huge plethora of possible candidates arise. As an example, all these boxes that you can see here. Of course, we have some requisites that all these candidates should fulfill in order to be our astrophysical dark matter, right? But once again, the theories can give you actually a huge number of candidates that can fulfill at least the requisites. For the remainder of the talk, and in order to finish today and not next week, we're going to focus on the WIMPs. Although also in my group, we have been working with other candidates, in particular the axions, the gravitino, and the axini, for instance, right? But once again, I'm going to focus on the WIMP, which comes from the weakly interactive massive particle and is the preferred candidate among all of them by far. Indeed, I would say 95%, yeah, something like that. 95% of the work that has been done in the last 3 decades or so, when it comes to dark matter searches, have been focusing on WIMPs, okay? For different considerations that I will be happy to discuss with you guys with a coffee, okay? Since we are astrophysicists here, let me just move on and give for granted that the WIMP is our candidate, right? And then I will explain to you how we have to use gamma rays to search for these WIMPs. The WIMPs actually have a very interesting property, according to my particle physics colleagues, and it's the fact that when they meet each other, they will annihilate, giving standard model products. Standard model products in different flavors. One of them can be actually gamma rays. Another one is neutrinos, and then you also have antimatter, some kind of charged particles, right? Like antideuterons, antiprotons, positrons, and so on. I will be focusing on gammas, as I already said, right? Which is by far the golden channel, as I like to call it, because we are most sensitive. We have very sensitive instruments in the gamma ray regime versus the things that we have, the instruments that we have in neutrinos, for instance. They are not competitive at all with gamma rays for these searches at the moment, at least. And also, charged particles has other problems. Being charged, right? They are deflected by the magnetic fields. And then it's difficult to know where these guys are coming from, right? While gammas actually just travel in a straight line, towards us. So that makes the whole thing much less complicated. Okay, so the idea here will be to look for the WIMPs by searching for these gamma rays coming from the annihilation of the WIMPs in high dense places of the universe, right? Where you expect the largest concentrations of WIMPs so that they meet with some frequency and annihilate. Fortunately, we have at the moment a huge plethora of instruments to perform these searches, both from the ground. Let me just mention a few ones here. LASSO, that recently came in operation from China. Then MAGIC, HESS, and VERITAS, the classical ones, 20 years more or less running at the moment. HOGE, also, US and Mexico. All these basically exploit the so-called Cherenkov technique to perform gamma ray astronomy from the ground. Again, I will be happy to tell you guys the details with a coffee. And then in orbit, we have the NASA Fermi LAT, Charlia instrument that was launched in 2008 and is still in operation, right? Nearly 18 years. It's nicely running still. So smoothly, we're smoothly running the instrument, and Fermi LAT has revolutionized the whole gamma ray field in these almost 20 years now. So once again, we look for these gamma ray WIMP annihilations, right, in gamma rays using all these instruments. Okay, so being a bit more quantitative about the annihilation flux that we expect in our instrument above a particular energy threshold here and a particular direction of the sky is basically given by the product of two terms. A first one that encapsulates all the astrophysical considerations in the game. I will be talking about that in a second. Oh, what can this be? Okay, there's supposed to be an equation here, guys. Okay, I will mention with words. It's very easy. Okay, so that's the first one, and then a second term which encloses all the particle physics that enter the game. In particular, and also the equation here is lost. Okay, very good. Yeah. Okay, so the particle physics term is basically given by the cross section of the annihilation over the mass of the WIMP that you consider to the square, and times the so-called annihilation spectrum with some particular branching ratio that will give you basically the channel, the particle physics channel through the annihilations are actually happening. Sorry about that, because there's an equation here, there's another one here, which are actually quite important. Anyways, here you can see, so it's number of photons per annihilation in this part, the cross-section of the interaction, as I was mentioning, the WIMP mass, and then the branching ratio that controls the channels for the annihilation. And then the J factor is just the line of sight of basically the integration along the line of sight of the dark matter density that you have to the square. To the square because we are talking about annihilations, right? So what matters is actually two particles, right? That's why it's actually to the square, no? Given the fact that this controls basically the over-normalization of the flux, as you can see, right? While this gives you more or less sets the typical spectrum that you will have. And you better look for these fluxes, annihilation fluxes, in those places of the universe, of course, with the highest dark matter densities, right? I mean, you basically are driven by the J factor number here, no? That you would like to use. And then with this in mind, where to search? Well, of course, you need, since we are talking about fluxes, you don't need to go, you don't want to go so far, right? Because otherwise the flux will drastically decrease. So you want to remain to keep, the search in the local volume, let's say, right? And actually we do our searches, when you do the calculations, what you find out is that what actually matters for the searches is something really, really local. I'm talking about the galactic center, for instance, the densest place in our galaxy, right? Some satellites of the Milky Way, the dwarf extraterrestrial galaxies that I will be talking about. Also some local galaxy clusters, because in this case they are very massive, although they are a bit farther, but still very massive. And why not some nearby galaxies like M31 and so on, right? So still, things that are relatively close to us and exhibit the highest dark matter densities, the highest dark matter concentrations, so that you basically have a large number in the J factor, right? Okay, so with this in mind, I already said, this is just to take a look at the gamma ray sky, the annihilation, the dark matter-induced gamma ray sky, if we had some glasses to see only the annihilations, right? This is, of course, coming from a simulation, a dark matter-only simulation. So the color here only corresponds to give you an idea of the density, no? The brightest the color, basically the densest is the object. So according to this kind of figures, you will immediately realize that the galactic center is actually our best target in principle, a priori, right? It outshines the rest of the things in the map. But there's also other possible targets like galaxy clusters, as I was saying, also dwarf galaxies here, even the Milky Way halo, the smooth distribution of the density within our galaxy, and so on. So we look low and high, over the years in all these potential targets, and the current status of the field, I can briefly summarize here. So we found no signal at all in our data, right? Basically, we did predictions, knowing the density, having an estimate of the density of the dark matter density in these objects, and plug in the particle physics factor, right? You end up with a prediction for the annihilation flux. You look for these flags in your data. We found nothing, as I said, but since you have a prediction, you can actually set some constraints on the dark matter particle models, no? The underlying models. As I said, no signals were found, although we have to fight with several claims in the community for many years. Actually, one of them still survives in the galactic sector, but that's another story. And now to be more quantitative, I will be more quantitative, but still part of my general introduction is just to give you guys an idea of the current status of the field in the relevant parameter space here. The parameter space that we use, that comes basically from the J factor equation that you couldn't see, right? It's just, it usually has to do with the cross-section versus the mass of the wheel. In this way, this is the cross-section of annihilation versus the mass. You know, in principle, the rest. You have your observation that sets you the minimum flux of your observation. You have something that has to do with the number of photons that you expect from the theory part, and then the J factors can come. I put here simulations, but can also come from observations if you have a determination of the underlying density profile in these objects, right? So you know everything once again, and let free the mass and the cross-section and mass of the wheel. And then, as I said, so we observe all these potential targets, no, for us with gamma rays. We found no signal, and then we proceed and set our limits by using this kind of equation here, this formula, right? Everything above these lines, every line will correspond to a particular upper limit, right? So everything above these lines will be excluded by your observation. Okay, so the status of the field is the following. Basically, what you can see is that there is a line here, this pink dashed line here, that controls, basically dominates the limits at the lowest wind masses. This line actually comes from the observation of dwarf galaxies with Fermi LAT. And then at around 1 TeV or so, there's actually a better line, a better constraint, right? That starts to be more competitive than the Fermi LAT one. And is set by Cherenkov telescopes from the ground, in particular the observation of the galactic center region with HESS data. Again, we found nothing, we set our constraints, right? How valuable, how important are these constraints? Well, you can read here what we call the thermal Rayleigh cross-section value, which is somehow it sets the goal of the whole search. This kind of value for the cross-section has a very particular meaning, a very important meaning in this kind of context, no, in this kind of searches. It refers to the cross-section that you need in order for these WIMPs to account for the whole dark matter content of the universe. So if the WIMP is actually our dark matter particle, no, in the universe, you expect the WIMPs to annihilate with this particular cross-section. You don't have a clue about the WIMP mass, but at least you know by the way the coupled in the early universe, at least you know from your models, right, from your WIMP models, that this is the cross-section of annihilation that should be for the WIMPs. So this is basically our goal. Our goal is really to perform observations and to set constraints in such a way that you can actually test the thermal Rayleigh cross-section value, which is the WIMP, the WIMP dark matter scenario at the end, right? As you can see, we only do that in a small, tiny region of the parameter space. Only Fermi LAT at the moment can test the so-called thermal WIMPs, the WIMPs that can actually account for the full dark matter content, while the rest is still totally unexplored. So there's still a lot of room to improve our analysis and to do further research, right? But this is basically what we want. Okay, so this is the more or less I thought it would be important for you guys to know more or less the status of the field, right? Because I understand that you guys are not working on this. So this is more or less the introduction. And today I would actually like to talk to explain to you guys the recent progress that we have made in the past years to understand the role of dark matter halo superstructure in setting all these limits. What was basically the role that all these subhalos play in the dark matter search game, no? When it comes to, once again, to set constraints and to look for signals out there. Okay, so what do we mean by dark matter halo substructure? Well, you know that given the structure formation, the way structure formation works in lambda CDM, right? Dark matter halos are full filled with a huge amount of subhalos, right, of superstructure that you can see here. For instance, this is coming from the G-halo simulation, a Milky Way dark matter only simulation. If I put actually the typical size of the Milky Way will be like this, right? The baryonic stuff is really located at the very center of the whole thing in this kind of scale, while there will be a whole, a huge dark matter halo surrounding, of course, the baryonic material. But not only, you can see that there's not only a smooth distribution all over the place, but actually you will expect a lot of clumps, a lot of subhalos here and there within the larger dark matter halo that basically we call Milky Way, right? Yeah, so this is this will be the characteristic visual radius of the object in this kind of picture coming from a snapshot ratio 0 of the simulation. And it is believed in lambda CDM, right, that the largest of these, the most massive of these subhalos will be hosting the dwarf galaxies, the satellite galaxies that we observe with our instruments, where there should be a huge population of smaller guys, smaller subhalos, all over the place, right, with masses below, let's say, 10 to the 7 solar masses or so, all the way down to the minimum expected subhalo mass of maybe Earth mass microhalos, 10 to the minus 6 or so solar masses. And as I said, they will be there, right, all over the place in millions, but you wouldn't see them. That's why I call them here dark satellites, because they are not massive enough to retain gas or stars at all, right? They are not massive enough to really, to bring gas and to basically form stars. So you wouldn't know where they are in principle, right? While again, dwarf galaxies will actually have an optical counterpart that we actually see with our telescopes. Okay. So, I mean, it is evident in this kind of lambda CDM framework, this picture, right, that all this dark matter halo substructure is going to play a key role when it comes to dark matter searches. On one hand, we have both the visible dwarf and the dark satellites are high dark matter dominated systems, and therefore they represent very good targets by themselves already, right, for our searches. Also, they are located, some of them are located really close to us, right? So you could actually be, I mean, the sun could be actually be here, right? And you expect a huge population of dark satellites, why not, surrounding us. But also some of these dwarf galaxies will be relatively close with just a few tens of kiloparsecs typically from us. When you do the computations of the J factor, actually they are very excellent targets, right? So yeah, that's one thing. Second thing, of course, if you compute the J factor for the smooth distribution of the whole object, it's going to differ a lot from any scenario in which you actually compute the same J factor, but now including all the annihilations happening within every clump, right? Also, remember, guys, that the J factor is proportional, the annihilation flux, no, is proportional to the square of the matter density, right? These clumps are very concentrated, which means that since you now go to the square of the matter density, right, it means that they are going to be particularly interesting, important, relevant in terms of annihilation flux. They are going to significantly boost your signal with respect to the smooth only computation, right? So this is what we call substructure boost or subhalo boost in the literature, and we have also made a lot of stuff in the past years regarding this. Today, I'm going to focus on dwarfs and dark satellites, right? With that again, they represent very good targets. And then I will be leaving basically for the next visit, if these guys allow me. I will leave for the next visit everything related to the subhalo boost, okay? Computation and, well, again, the impact of all of this. But let me just say here that indeed they are particularly important. They are critical right now when it comes to the J factor computation for many objects out there. Okay, so let's start with the dwarf galaxies. As I was saying, I will be focusing on the searches that we do for both dwarfs and dark satellites. Dwarf satellite galaxies, actually, they represent the most dark matter dominated systems that we know in the universe. The inferred mass to light ratios are huge, in some cases up to 1,000 or so. Although, well, there is some controversy because they are subject to large systematics in many cases, but still, I think it's fair to say that they are actually the most dramatic dominated systems that we know in the universe. And therefore, this is perfect, of course, when it comes to dark matter searches. Also because some of them are really close to us. Indeed, we have several within the 50 kiloparsecs surrounding us. We have many of them. We have something like 52 or so confirmed dwarf galaxies at the moment. And more around the way. I put here this because we have many other candidates, but still, they will need some special confirmation in order to disentangle, to really, confirm the true nature of these objects being dwarfs and not something else like star clusters or globular clusters, right? So this is coming up, but in any case, we have already a large enough sample to play with. And more importantly, when it comes to gamma ray dark matter searches, these objects are let's say, very bored from the astrophysical point of view, right? There's really nothing going on there. Like, for instance, there's no star formation, relevant star formation anymore, not even supernovae. So there's really nothing happening from the astrophysical point of view. That's why I said they are like very boring objects for the typical, astrophysics, let's say, right? But this is actually very good news, because when it comes to gamma ray dark matter searches, they are very clean targets, right? So you don't expect gamma rays coming from conventional astrophysics at all. Whatever signal you may find in these objects, you can actually think about something exotic, because once again, you don't expect gamma rays, from any other conventional astrophysical processes, right?
Miguel, sorry, in this context, maybe can you tell us a bit about the current limits in the galactic center? So that there is confusion, there are a lot of gamma ray sources there, and
yes, exactly. I will briefly mention that in the context of the dwarf galaxies in a second. But what I can tell you is the following, right? I mean, in principle, a priori, as I was saying at the beginning of the talk, the galactic center represents the best target. When you do the calculations, right, despite the uncertainties in the density profile of the Milky Way, that's really the place that you want to go, right? The problem is that gamma rays, I mean, there are different physical processes that can give you gamma rays, right? And all of them have to do with relativistic particles, in terms of velocities, interacting with the medium. For instance, Restralum, inverse quantum, pi-zero proton-proton interactions, things like that, right? In the galactic center, you have a huge density of many things, right? Of gas, of stars. So it's a very crowded region. And this actually means that by all these processes that I'm mentioning, that can generate gamma rays, you will have a superposition of gamma ray emissions coming from many different processes going on in that part of the galaxy, in that very busy region of the galaxy. So when we try to model all those emissions according to our best knowledge of the region, right? What happens is that we end up with some kind of excess with respect to these best models that we have to describe all that emission. So basically, you build your models, right? You go to the data, compare to the data, fit actually to the data, and there's always some kind of excess that remains in our data after subtracting everything that you know, right? This is the so-called galactic center excess, no? And this excess is very controversial, of course, but the reality is that, of course, it is there, that for sure, it's robust. And there are different explanations for that. Some of these explanations involve exotic physics, like dark matter. I think it's fair to say that after 15 years of seeing the excess and characterizing the excess, dark matter can be still a possibility, right? That's fair to say. But there's also other possible explanations, in particular millisecond pulsars, that can give you a signal as the one that we see for the excess. So actually, I was going to mention all of that in a second, and I'm going to do it in any case, because dwarf galaxies can give you an independent test, something very clean, a very clean target that can actually put at test the excess of the galactic center, in the galactic center as being due to dark matter annihilations because of that, right? You want to go to other more clean regions, right, where you can put at test this hypothesis, right? And this is what we do with dwarf galaxies. That's why they are so important. Okay. So how do we very quick. So how do we compute the J factors for the dwarf galaxies? Actually, what people do is to infer the underlying the matter density profile in these objects by using the kinematics of the member stars, no? in these dwarf galaxies, right? You basically take a look at the velocity expression of the stars, and then by using the Jeans equations that relate the potential, the gravitational potential to the light, basically to what you see, to all these measurements of the stars, you infer, as I said, the matter density profile, and then the J factor is just, as you know already, the square of this dark matter density, no? This is the way we compute the J factors. Here you can see the typical numbers in log versus the distance to each of these dwarfs for a sample of dwarfs that are very well characterized, I would say. They come in different kinds here. I don't want to go into the details. Classical dwarfs are the ones that we know since many decades ago. Ultra faint are recently discovered dwarfs. And then, as you can see, basically the J factor, which by the way has a significant uncertainty, because there are several things that can actually give you a very large uncertainty in some of the cases. But anyways, this J factor behaves nicely, right? And basically it goes up, it decreases as the inverse of the square of the distance, because we're talking about fluxes after all, right? What we do is to parameterize all this to come up with some kind of prediction for the J factor that will be basically depending on the distance of the object. It's actually very useful when it comes to dwarf galaxies that are recently discovered, for which we still don't know, the J factor, because we don't have spectroscopic measurements yet. So we can quickly use this kind of recipes to have at least an estimate, first order estimate of the J factor for this object. Okay, so this is the way we have we compute the J factors for the galaxies. So then Fermi LAT, we have been exploring these candidates, these dwarfs, in the context of the matter searches for a long time, since the beginning of the mission. Just I want to tell you here the last word that we have regarding this. This is the so-called legacy dwarf dark matter analysis that we put together a couple of years ago, a bit more on that now. By using a sample of 50 dwarfs, basically all the dwarfs that we have available at the moment in the literature. We look at the direction of these 50 dwarfs. We analyzed carefully all the data coming from the satellite, in the direction of these dwarfs, and we found no gamma ray signal at all above our models, right? So what we did was the usual thing. You don't find a signal, you proceed and set your limits, on the sigma b versus mass parameter space. This is what I say here, right? You have the upper limits to the gamma ray flux in the region, and then you basically translate all this information, these upper limits to the flux, into the dark matter parameter space. And you can see here, basically the last word. This is the last word of the Fermi LAT collaboration on this thing. Just to put these things into context, guys, these are the most robust, the best limits in the literature in gamma ray dark matter searches so far, okay? Not only from dwarfs, from any other target, okay? These are the best limits that we have at the moment. The same parameter space that I showed you before, cross-section versus mass. This is the thermal Rayleigh cross-section, basically the goal of all this search. And as you can see, our limits, well, there are several lines here. Let's just focus on the solid black line, which is the one coming from the actual data. As you can see, we start to rule out thermal winds below 100 GeV or so. This is a very interesting result, because it tells you basically that if the wind composes the dark matter in the universe, the total dark matter content on the universe, the wind must have masses above 100 GeV, right? So this kind of analysis rule out lighter masses. By the way, there is something else here that is also it relates to Silvia's question, right? Which are these blobs here that you can see, in the figure, right? These blobs are actually coming from a different analysis, and they correspond to the cross-section and the mass of a signal in the galactic center, this excess of the galactic center, if interpreted in terms of dark matter, right? The matter annihilations. So if you believe that the excess of gamma rays coming from the galactic center are due to WIMP annihilations, these WIMPs will have a mass of 10 GeVs or 10 GeVs or so, sorry, and a cross section which is more or less in the right ballpark around the thermal radius, right? Why the dwarf galaxies are then so important? Because they are the only targets at the moment that can actually provide an independent test of this signal as due to dark matter annihilation. As you can see, there's a tension, I will say, in the best case scenario. There's a tension between the claims of the galactic center excess as due to dark matter annihilations and our limits set with the dwarf galaxies, right? In order to be totally fair with you guys, totally honest with you guys, I would say there's a mild tension. These kind of blobs here are only typically at the 1 sigma and 2 sigma level. So if you go to something which is no 1 or 2 but 25 sigma, the blob will be much bigger, right? And also our limits are subject to, although very robust, they are subject to factor 2 uncertainty or so. I think that would be more or less the way to put it. So all of this to say that there's still room for this to happen, and the dwarf galaxies don't totally exclude this possibility, the possibility of the galactic center excess as due to dark matter. Okay, given the certainties in the game. Okay, I'm going to skip this one. Yes, so an extension of these searches on dwarf galaxies was also recently made by some of us in a recent paper last year, and it's the fact that we understood basically that we could also use stellar streams, the so-called stellar streams, to search for these dark matter annihilations. The idea here is very easy, right? It's very simple. Some of the progenitors of these stellar streams are known to be dwarfs. And as dwarfs, of course, they are going to have a non-negligible content of dark matter in their cores. And this is basically something that we explored in this kind of studies, right? So the idea, once again, is that you have a dwarf galaxy that enters the tidal field of the Milky Way, creating a stellar stream, over the cosmic time, right? But still at the core of the stellar stream, there will be a significant amount of dark matter that you can actually use for your dark matter searches, right? Of course, there are significant uncertainties in the game in this case, right? Because knowing the dark matter content in the core of this stellar stream is not something easy. So we did our best to model all of that, coming from numerical simulations too, and also, of course, by contrasting with the observations that we have on the streams. So basically, what we did was to end up with a sample of order 10 streams for this kind of searches, and we set competitive dark matter constraints on the same parameter space using these objects, right? Here you can see the individual limits, and then by combining them, you end up with a solid, by combining them in a statistical way, using a combined likelihood analysis, you end up with a solid black line here. But as I said, there are large uncertainties in the game, so we play with different assumptions on the dark matter distribution in the objects, with different possibilities. And so I think more or less a fair estimate of the systematic uncertainties will be something like this, right? Which, as you see, spans over 2 orders of magnitude in the uncertainty. All of this basically to show that at least these objects may have the potential to have an important role in dark matter searches in the future, provided that you actually are able to understand your systematics in a good way, right? Okay, so now let me take a look at the. So how much time? Totally lost.
10 minutes.
Sorry?
10 minutes.
10 minutes. Okay, that's perfect. Thank you.
Can I ask something else?
Please.
So what's the precision of the position in the sky?
Yes, we have an angular resolution of around 0.1 degrees, so 10 arc minutes. Okay. To be compared to optical or radio, whatever, right? So there's something else, but still, I don't know why are you mentioning this? But for instance, in the case of the dwarf galaxies, this basically means this 0.1 degrees or so. It means that when computing the J factor, you will have to integrate, of course, the J factor within 0.1 degrees, right? And this is totally fine. These kind of objects, the scale radius of these objects are typically something like 0.3 to 0.5 degrees or so for the objects in our sample. It means basically that if they were to be extended, we will actually see some extension, for instance, right? Okay. Anyways, all this is properly computed in the predictions.
But this is with Fermi, no?
This is with Fermi.
Yeah, so the ground-based, what is the...
So, okay, so they are comparable. For magic, Hess, for instance, is around 0.1 degrees or so. For Hawk and Lasso at the highest energies, tens of TeVs or so, it's actually significantly worse than that, around even 1 degree or so. But then in the future, there will be a revolution. Cherenkov telescope array, right? CTA. We have an angular solution of around 0.03 degrees. So factor 3 better than the current instruments. Hopefully, let's see.
Okay.
Yeah. The problem, we can maybe chat afterwards, but the problem is really the way the detection technique works. No, it's something really attached to the technology, basically. So we use Fermi LAT, for instance, is a pre-production telescope. You cannot collect gamma rays with a mirror or with a lens, right? There's no way to focus them, right? Given the frequencies, no? So basically what we do is to convert the gamma ray within the tracker with some kind of layers of unoptimized material. It's tungsten and silicon. And then you basically the gamma ray interacts with these layers in the tracker, and then it will generate a pair of electron and a positron that we track.
Yeah.
We measure the energy and this direction, and then you can reconstruct the incident gamma ray, the energy and the direction. But this has some limitations, very severe limitations when it comes to angular resolution.
Does it depend on the energy of the particle?
It does, and very strongly. What I told you, 0.1 degrees is actually at best. So that happens already in the GeV regime. In the sub-GeV regime, Fermi LAT, for instance, at 100 MeVs, and don't laugh. Well, you can laugh. At 100 MeVs, we have an angular resolution of around 15 degrees. But it's strongly dependent with energy, and as soon as you go to higher energies, you can actually do much better, up to 0.1 degrees or so, above 1 GeV. There's a plateau there. Okay. Okay, yeah, please, let's do this more dynamic. I know I have only 10 minutes, maybe a bit less already, but it's always more fun if you have questions. Okay, please.
Yeah. Yes. Out of curiosity, if you put kind of the limits, the best limits, how many gamma ray photons are we talking about over the 10 years?
The 10 years.
That you would have expected, I guess, 1 gamma ray photon coming from dark matter, 10, 100 million?
It's around like a few tens of photons for the best candidate that we have per year.
1 photon per year, per decade. So, and what is the...
we count individual photons in gamma rays, of course.
So then I was wondering about the variability. So what is the pattern and variability that you would expect for dark matter?
From dark matter, steady source. Totally steady source. So in the 18 years of data, basically you don't expect any kind of change. You have the density, in the core, right, of the objects, and of course there will be annihilations happening, and this will basically erase the cusp somehow, right? Yeah. But at the scale that we're talking here, that's totally irrelevant.
I was thinking more on for the J factor that you might have, like this, maybe tens of kilometers per second movement of subhalos that might merge with each other. I don't know if that would create something. But if not, then wouldn't that be a way of distinguishing astrophysical from dark matter source origin in the...
Okay, well, indeed, one of the filters that I'm going to talk about, for dark satellites, one of the filters that we perform, of course, is this variability study, So if we see something variable, we actually reject it. We believe this is not dark matter. It may be something else. The gamma ray sky is highly variable, right? So pulsars, AGNs, of course, all of that exhibit a huge frequency variation.
So the Milky Way center excess is actually...
it's a steady source. It's a steady source.
So you don't see any variation?
No variation at all.
Second pulsars?
For the second pulsars, it's totally fine. No, it's totally fine. You don't expect a pulsation in the gamma ray regime for these objects. Yeah, it's totally compatible with being millisecond pulsars at the moment. So variable, the periodicity there is not going to give you any clue. right?
But it's because the cadence of the observations, or do you expect them to do you have so many that they average out?
Yeah, well, for some, we know pulsars that actually are intrinsically variable in principle in gamma rays, but the period is so short, microseconds or milliseconds, right? From micro to milliseconds, that you are not sensitive at all. So what you expect in gamma rays is actually something totally integrated out, basically. So you have a steady emission, right? In some other cases, actually, it's more complicated than that. We do see, you don't expect that, you expect some variation in radio, for instance, so periodicity, of course, because they are pulsars, but you don't expect such a variation in the gamma ray regime because of basically the beam, no? The way the beam behaves and so on. You see a totally different region in the gamma ray regime, right? So it's a bit more complicated than that, but this has been exploited, and well, it's totally compatible at the moment. These excesses due to millisecond pulsars, either millisecond pulsars or dark matter. Yeah, welcome. Okay. Yes, so let me talk a bit about that satellite search. These tiny guys that I was mentioning at the beginning, right? In this lambda CDM structure formation, whatever scenario, right? With lots of millions of dark satellites being in a galaxy like our own, but we know optical counterparts, no? So how the hell can we, just search for these dark satellites if we don't know where they are, no? Okay, so the connection that you guys have to make in this case is the following. The thing is that there is in all our catalogs, in all our gamma ray catalogs, not only Fermi LAT, by the way, but actually ground-based Cherenkov telescopes catalogs, right? In all the gamma ray catalogs that we have been performing over the last couple of decades, we always end up with something like around 1/3 of the objects in the catalog, which are not associated to anything that we know. So they are basically unknown in origin. We don't know what they are, right? This is not a small number, right? In the case of Cherenkov telescopes, we are talking about a few tens, that's true. But in the case of Fermi LAT, where we have something like more than 7,000 objects discovered at the moment, right? In our latest 4FGL DF4 Fermi LAT catalog since a couple of years ago. We are talking about something like 2,500 UNIDs, unidentified objects, as we're going to call it from now on. Okay? So once again, 2,500 objects that we don't know what they are at all, right? We don't have a clue. In many cases, to put it, to give you an example about why we end up with such a large amount of UNIDs, in many cases, what is going to happen is that given the angular resolution, the poor angular resolution that we have, right, we end up with we cannot firmly associate our gamma ray signal to a particular object in the field of view. So you have a block like this, 0.1 degrees, right? And within this 0.1 degrees of gamma ray emission, no, our BSF, right? You have many galaxies, different pulsars, whatever, and you cannot firmly associate the gamma ray emission to any of them. So this remains as this is cataloged as an ID for us, right? But in several other cases, this is not the case. In several other cases, you have a gamma ray emission, 0.1 degrees blob, no, in the sky, and there's nothing there, right? We don't really know what they are. What I'm going to do here is, to put on the table this exciting possibility that some of these NIDs may be actually dark satellites annihilating to gammas in such a way that we actually see them, provided that they are close enough, no, to us and they are massive enough. You may end up with a flux which could be significant and could be detectable by Fermi LAT. So maybe, among these 2,500 NIDs, you have a dark satellite hidden in this pool of NIDs. Why not, right? So this is what my group and I have been working on for many years now by developing some, a specific pipeline to pinpoint those NIDs that may be compatible with dark matter annihilations in the way we know, right? If you believe on the WIMP, these NIDs, if they are due to WIMP annihilations, they should exhibit some particular spectral properties and also spatial properties, right? So basically, we go NID by NID in the catalog and look for those that are compatible with what we expect from dark matter annihilation. This is what I call here these filters. No, we developed a series of filters, some of them actually based on variability too, right? To exploit this possibility. By doing that, you may end up with within different scenarios. You may have a few VIP candidates, no, which exhibit very nice properties in terms of dark matter. They are compatible with what you expect from dark matter. Also, of course, you have to take into account that for many of these NIDs, we have large error bars in the spectrum, right? And also spatial morphology is not totally well characterized. And that basically, given the systematic uncertainties that you have in this analysis, some of them actually survive or are, look like very good dramatic candidates also because of this, because you have large error bars and you can easily accommodate, let's say, some dark matter models, right? So anyways, for this very good, the best candidates that you may have, you can actually perform an even more dedicated data analysis. There are ways to do it more sophisticated. We have been doing that already for a few of them. Or maybe to do some follow-up campaigns at higher energies with Cherenkov telescopes, lower energies with X-rays, in radio, optical, blah, 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 right? By doing that, actually, you can, for instance, if you see an emission in X-rays, you don't expect this from dark matter, from WIMP annihilations, so you basically neglect, you reject, discard this object as due to dark matter, and so on. Second scenario, you have, given the uncertainties that you have, as I said, right, you may end up with a few more subhalo candidates. Yet uncertain, they are not really VIP candidates. In that case, you can actually use them to set dark matter constraints. I'm going to show you how we do that. In the worst case scenario, apparently, at least a priori, right, you find after applying all these filters on your pool of NIDs, you end up with no NIDs compatible with dark matter at all. But in that case, even in that case, I will show you that you can actually achieve the best constraints, dark matter constraints given by the method. So it's a win-win thing, right? So okay, no dark matter, that's true. But at the same time, I will be able to set the best constraints. How do we do that? By shortly speaking, right? To put a long story short, what we do is to compare our predictions coming from numerical simulations, where you, of course, can infer dark satellite J factors, the number density of them, spatial extension, whatever you want, because they are simulations, you know everything. You compare these predictions, accurate predictions, and about the dark satellite population with your actual pool of NIDs in your set gamma ray scan. You actually convolve all of this with instrumental sensitivity and so on. And then what you do is to after performing this kind of predictions and convolution with the instrumental sensitivity, you have a number of detectable subhalos, basically what you expect, for Fermi LAT, and go to your gamma rays, to actual gamma ray sky, and just compare the numbers, right? Just to put things simple, and this is the way you actually set the constraints. So imagine that you after performing this kind of game here, right, you end up with a prediction of okay, Fermi LAT should see 100 subhalos, 100 dark satellites, no? But then I go to my pool of NIDs, and after performing all my filters, I only see at most 10 NIDs compatible with dark matter. I was saying that I should see 100 with Fermi LAT. I only have 10 at most. By performing this kind of comparison, of course, intuitively you can already imagine how this can translate into dark matter constraints, right? The less objects you have, the less NIDs you have that could be compatible with dark matter, the more stringent will be this game, with the comparison with your predictions. So
what subhalo mass contribute the most to the?
That's a very good question. I have it somewhere. I can go quickly here. So this is coming from one of the simulations, right? I show here the J factor versus the distance to the Earth, and also here in the Z-axis you have the mass of these guys. Okay, so as you can see, the highest J factors actually will correspond to very massive objects, right? Which are basically will correspond to the dwarf galaxies, right? Because these are already visible, 10 to the 9, 10 to the 8 or so, right? But there's still a few points here and there with very low masses, 10 to the 5, 10 to the 4. So some of these dark satellites, in principle, right, below 10 to the 7 or so, should have J factors which are comparable to the dwarf galaxies. For instance, the ones that dominate the most, probably the peak, as you can see, is around 10 to the 7, 10 to the 8. So,
but you claim that there are dark subhalos of 10 to the 9 at 1 kiloparsec from the Earth?
You mean this 10 kiloparsec?
No, 1 kiloparsec. These points at 1 kiloparsec up, the ones highest, even higher.
No,
those three
well,
points
this one, we know this in some of our realizations. We actually see very massive subhalos very close by. And that's something that doesn't show up in our more recent simulations based in Auriga. But at this moment, I also noticed this thing.
Most of them would be tidally disrupted by the Milky Way disk.
We applied. I mean, this is coming from the simulation itself, huh?
But with baryons and this.
No, not in this case.
Yeah, that's what I meant. Like probably you have gravity only, but if you had baryons, then
yes. So this
destroy all those.
Absolutely. This work is based on Galaxy 2, right? This is this one, I think. Now we had the same work with Auriga simulations, and we don't see these guys anymore.
Yeah, that makes sense.
Yeah.
So I guess the most likely unidentified source would be a smaller mass.
It could be. Well, this is what I was always hoping, right? So I think it's fair to say that there are things of around 10 to the 5, 10 to the 6 solar masses, which can actually dominate the J-factor distribution. By the way, this I didn't say, but that's why I told you that these are only happening for a few realizations, because this is coming from, these are the 500 brightest subhalos in 1,000 realizations, right? So only in a few of them, right? We had this kind of issue back in the day that it doesn't show up at the moment in the Auriga-based work that we have. Yeah. Anyways, it's very exciting, right? That some of the dark satellites could actually yield the highest dark matter signals. That's something that we wanted to understand, right? Okay, so
it would be great if we can come soon to the end.
Yes.
We're already slightly over time.
Okay, very good. I will do so. I don't want to go into the details because then I will go really over the time. Let me just say that we applied all this machinery that I was mentioning here, right, to the latest Fermi LAT catalogs. For instance, in this couple of works, now we are working on the latest Fermi LAT catalog. We're about to have the paper ready. And I wanted to tell you to show you how these constraints coming from this kind of from different catalogs, let's say, compare to the limits coming from the dwarf galaxies, for instance, in the same parameter space. You have the same parameter space here, the cross section versus mass. This is our limit coming from this method, and as you can see, they're actually very nicely competitive and comparable to the one coming from the dwarf galaxies, which is this one in this case. Okay. So a very independent method using a different target that can actually set very interesting constraints. I can just anticipate too, but that by using the latest pool of NIDs in the latest catalog, we are actually going much farther in this parameter space. We are basically recovering something very close to the one of the dwarfs. So again, very competitive, in principle, very competitive method. Of course, all this relies, I'm going to skip this. I'm going to try to be qualitative here and just give you the take-home messages. So of course, all this work, as we were mentioning, right, relies heavily on the numerical simulation work that you do. So in order to set the constraints, now you will need to trust your numerical simulation work. Of course, that's why it's so important to do all of this in a high degree of detail. And this is something that we have been doing over the years, basically characterizing the subhalo population, the different ingredients that describe the subhalo population in a galaxy like our own Milky Way. And well, we basically are driving somehow our search, learning from all this numerical work. We have been doing a lot of this work in the last years for several different aspects of the subhalo population. I wanted to tell you guys a bit about some of the most recent work that we have been doing. By the way, Raúl is here too, and Jens. I guess some of you also know Jens. This was a lot of fun. I will be happy to chat about this. So anyways, just again, characterizing the whole subhalo population in different ways so that we can learn more and more and have more accurate predictions for the J-factor of the dark satellites and the dwarf galaxies. Why not? Basically, they are subhalos too, so that we can actually place very robust dark matter limits in the relevant dark matter parameter space. That's the idea, right? This is the work I was referring to. Raúl, maybe we can talk about this. Basically, in our recent work that we just put in the archive in January, a former student of mine and also a former student of mine too, a postdoc, Alejandra, We have been basically using Auriga to revisit the whole game, also on the different prescriptions of the subhalo population. Now we play with resilient and fragile prescriptions for the subhalos themselves, and we take a look at the implications in terms of the dark matter constraints here. Okay, so take home message from my talk. Coming back to all these possible targets, no, for gamma ray dark matter searches, and more in general for indirect dark matter searches, I will say that in the state-of-the-art analysis is crucial, is key to include to account for the role of the dark matter substructure, because I expect this to be an ingredient which is relevant for all the searches. I put most, but I would say for basically all of the objects that you can see here. But maybe the galactic center, where this is not so relevant, maybe substructure is actually going to play a key role in all of this. I leave it. I actually go here and just say thanks. Thank you so much.
Thank you for your nice talk. Yeah, we're already over time. Definitely very important, good question.
Sorry, guys.
I guess we can have this, but otherwise, I believe there's more time for questions.
Yes, please. I'm in the office 102. I will be around until tomorrow afternoon. So yeah, feel free to come and to chat with me, of course. I don't know if there is any pressing question now.
I could ask more things, but we can also keep one.
Yeah, well,
do it.
it's already past one, right? So
All right, as you
it's
wish.
easy,
You're the boss.
I'll go.
We should have, yeah.
At least let's take one, Maurice, please.
Yeah.
That's one.
Oh, yeah, so this.
Okay, yeah, please.
Yes, I guess we anyway go.
Important.
I guess we also go together for lunch, right? And can continue discussion there. But yeah, please
That's true,
just
that's
ask.
No, I was just wondering about the spectral, sorry, the change with frequency. So with energy, think about frequency, think about energies. Right?
Yes.
So because
You mean
that
for the
blob,
matter?
yeah. So that, well, if that tells you something about the origin, right? So that blob
Absolutely, of course.
is only at a given mass, at a given energy, right?
Yes, because let me see if I have something about that here. Maybe I'm not sure. Is too. Oh yeah, great. Okay, this is actually it can be useful. So this is all theory, okay? So if you talk to the particle physics guys, they will tell you the WIMP can annihilate through different channels, what they call channels. No, it has to do with the particles that you will produce. So there are like two different families of channels, I would say. The hadronic ones, which are the curved ones here, right? That will give you actually a curved spectrum. And then the so-called leptonic ones that comes in different flavors, but basically it's a harder spectrum, right, as you can see. And this is basically what you're looking for, right? You have a prediction for the spectral energy distribution in gamma rays. Given this is this is an sample for a particular mass, right? So for this mass, you see, you know what you're looking for.
Right.
You're looking for well, of course, you have to marry to a particular channel, or you can do the analysis for all the different channels, as we do, right? But in any case, you have a clear prediction of how the spectrum should behave for these WIMP annihilations for the different masses and channels.
Yeah.
So you put that to test and apply to the gamma ray, to the galactic center excess. You end up with a best fit that has to do with a mass of around tens of GeVs, let's say, and a cross-section and normalization of the full spectrum, which is exactly within factor 2, the thermal one. So, I mean, it makes sense. It's totally reasonable in that sense. But of course, we fully exploit the spectral information. I mean, it drives the whole search.
Right, and also for the other sources, right? Contaminating sources.
Absolutely. There are no objects astrophysical objects in the gamma ray sky. I don't know, stuff from regions, AGNs, pulsars. There's nothing that can mimic an annihilation spectrum, but the millisecond pulsars below 50 GeVs or so. Okay. Above 50 GeVs, the millisecond pulsar, the mechanism that drives the gamma ray emission in millisecond pulsars cannot account for the emission. So they cannot reach energies above 50 GeVs. But below 50 GeVs, which is actually what we have in the galactic center. Below 50 GeVs, they can mimic this kind of spectrum. Yeah, I have it here, indeed. Pulsar spectrum. This is actually an actual pulsar spectrum. I chose here a particular millisecond pulsar that we see, right, in solid, and I overimposed the annihilation spectrum for a particular channel